Hello everyone, and welcome to our webinar today, Expressing Parallelism in C++ with Threading Building Blocks. Our presenter today is Mike Voss, who is a principal engineer with the Core and Visual Computing Group here at Intel. Throughout Mike's presentation, feel free to send in any questions you may have, and we will get to as many of them as we can at the end of his presentation. And we appreciate you joining us today, and we will now turn the time over to Mike.
Hi, thank you, and thanks for joining us today. So talking about threading building blocks, which is a C++ library designed to help simplify the task of adding parallelism to your applications. This lets you take advantage of all the resources, all the CPUs on a device and across multiple devices with additional features we've added recently for heterogeneity. What's attractive about TBB is it gives you good performance, high performance, it has easy to use APIs, gets you a faster time to market, and your code will be production ready. TBB is a library. It is available both as part of Intel Parallel Studio XE, Intel System Studio, and there's also a free tools program, and it's also available through an open source website, threadingbuildingblocks.org. When you get one of the pre-packaged, pre-built versions of TBB through Parallel Studio or through the free tools program, these will have been pre-built and optimized for Intel processors. There's support for Linux, Windows, Android, MacOS, and TBB is good for a wide range of domains. So many different kinds of applications, from animation to HPC to artificial intelligence to medical applications, have been successfully expressed using Intel threading building blocks. About threading building blocks is not only that it makes threading easy, but when you express parallelism using TBB, that parallelism is also composable. And this is an important part of why choosing TBB is a good choice. Composability means you can widely express the parallelism in your applications, and the TBB library executes this parallelism efficiently. So this means you can nest parallelism within other parallelism. You can combine different software components that use TBB to express parallelism, and you're not going to bog your system down by oversubscribing the hardware. This is not true of all programming models. For example, some models like the OpenMP API create additional teams of threads at each parallel region, and so you can easily oversubscribe your system if you're not careful. And this can lead to additional overheads as the operating system has to do the scheduling of these many threads onto the few cores that you might have. TBB, in contrast, uses tasks, and tasks are scheduled into a single thread pool that's controlled by the library, and so you get composable parallelism. And I'll go into more detail about this during the presentation. The other advantage you get with composable parallelism offered by TBB is your application will be friendly to other parallel applications. Now, TBB isn't aware of every other kind of application running on your system, but it itself is not going to be greedily consuming resources while it's idle, and it's not going to oversubscribe your system, which means that TBB will be friendly and be a good citizen with respect to other parallel applications running on your system. TBB is a set of building blocks for expressing parallelism, and we can roughly categorize these building blocks into two large groups. There are building blocks that are for expressing parallelism, and we have different kinds of high-level parallel execution interfaces. We have generic parallel patterns, we have this flow graph API, and we have also an interface called Parallel STL. All of these parallel execution interfaces are built on top of lower-level interfaces that make them composable with each other and allow efficient execution on your cores. The other large set of features provided by TBB are interfaces that are independent of the execution model. So these are other features that are useful in threaded and parallel applications, but they can be used regardless of the way you're expressing parallelism. So if you're using OpenMP to do your threading or native threads to do your threading, you can still make use of these features like our concurrent containers, our scalable memory allocator, and some of our other primitives and utilities. One of the things over time that we have noticed in real applications is that they actually have multiple levels of parallelism, and exploiting all of the parallelism in an application is necessary to get the highest performance. So typically we'll see in applications that there is a high-level task or message passing layer to an application even within shared memory. So these look like the coarse-grained computations in your applications, and they communicate explicitly with each other through messages. And then below that there's a fork join layer that captures your parallel loops that you execute using threading. And then below that level there's a SIMD layer that's best exploited using vectorization. Now TBB, as I mentioned on the previous slide, provides different high-level execution interfaces. And the reason is these more naturally map to one layer or the other. So for example, our Flow Graph API is very good at capturing this high-level task parallelism. Our generic parallel algorithms and patterns, as well as Parallel STL, is good at capturing this fork join layer. And Parallel STL, when used with particular execution policies, and I'll discuss those later, is good at expressing SIMD parallelism that's executed on the vector units within your cores. And again, what is beneficial about using TBB to express all these different layers within your application is because you have one library and one thread pool on which all of this parallelism is executing. This results in composable parallelism, where you get really good, efficient execution without oversubscribing the resources on your platform. So I'm going to walk through some of the large building blocks in TBB and talk about them in more detail. So I'm going to start with the parallel patterns. These are the ones that are good at expressing fork join parallelism that look like, typically you will think of these as loop level parallelism. So here's an example of a serial application that contains a lot of parallelism. It's not yet expressed. So we see here at the bottom we have this doubly nested for loop, and what this application is doing is it's creating the calculating whether or not particular points in the complex plane are part of a Mandelbrot set or not. And then the output is plotted, as you can see on the top right corner. In this bottom doubly nested loop, we have two loops, an I loop and a J loop, and they invoke this function Mandel. And this is what is called an embarrassingly parallel problem. Each invocation of this Mandel function can be computed independently and in parallel. So with TBB, we express this by using a parallel loop. So we just take this outer loop that's iterating from 0 to max row, and we can use one of the functions that are provided by our parallel functions, our generic parallel algorithms. For a second, we can use one of our generic parallel algorithms, parallel 4, to express this parallel algorithm. So here we're making a function call into the TBB library. The function is parallel 4. What we pass to it is the iteration space. So we say we want to iterate from 0 to max row. And then we provide the work we want to do on each value in that range from 0 to max row. We express this using C++ lambda functions. So TBB is a C++ library, and it depends on C++ features like lambda expressions and templates. So here we're using a lambda expression to capture the work we want to be applied at each value within that range 0 to max row. So within each value within that range, we're going to execute the inner loop, j equals 0 to max column, and we're going to call the Mandel function. So what happens underneath this is the TBB library will divide up this range, 0 to max row, into appropriately sized chunks, and then schedule these chunks of work and this lambda expression to be executed in parallel on one of your cores. So the TBB library provides a wide range of parallel algorithms, including things like parallel loops, like parallel for, parallel reduce and scan, parallel sorting, functions that are useful for doing functional parallelism, like parallel invoke, some that are good at streaming data, like parallel do and for each, where you don't know the extent of your iteration space ahead of time. These are very common patterns that are used in parallel programming. So TBB provides these common patterns and then implements them on top of TBB tasks. Now, I'm going to, at this point, talk a little bit about composability and why choosing TBB is a good choice because you get composable parallelism. So, as I've said, TBB provides many different algorithms, and you can combine those, and that's typically what would happen in a parallel application. You might have multiple loops in your application. You may have functions where you express parallelism, and in the body of a parallel loop you invoke another function, which it itself may express parallelism. So you may wind up having a bunch of software components all expressing parallelism, and you combine these together to make your application. So you can have different ways you compose software. One common way is through nesting, as I've just described. You have some function, it's executing something in parallel, it invokes another function, which in turn executes something in parallel. You could also have concurrent composition, where you just have two threads or two applications, and these themselves express parallelism. And you could just have serial composition, where you have a parallel algorithm you execute, and when it's finished you go on and you execute another. And it's important when you're building an application that you can compose these things in an efficient way. And TBB from the very beginning was architected to allow for composable parallelism, knowing that these kinds of combinations of software components would occur. And this is not true of all programming models. As a slightly more concrete example, nested parallelism. So nested parallelism, you could imagine you have some function at the top. It has a parallel loop where it's executing things in parallel, and each iteration of the loop in turn calls some function which also has a parallel loop executing things in parallel, and so on. Now this is great if you're just thinking about how much parallelism you are expressing. You are providing a lot of parallel work to do. So this could lead to an exponential growth in the available parallelism, and that's great. Unless, of course, your library can't handle this much parallelism, and there are some models that cannot. So for example, if each piece of work becomes its own OS thread, then you could bog down your system, causing the OS to have to do a lot of work to schedule these threads across your available hardware resources. Now in TBB, we do a good job of this scheduling. And the reason there are several features in TBB, those low-level features, on which all of our high-level interfaces are built. So TBB is a composable library for several reasons. First is because it uses tasks. So tasks are lightweight C++ objects. Typically, we're not creating these directly. We're just expressing a loop that has a body using one of our parallel algorithms. But underneath it, TBB is creating a task. And what it's doing is it's creating a C++ object that represents a piece of work to do in parallel. And so these might be things like it captures the variables that it needs. It has the arguments, and it has your lambda expression. That could be considered a TBB task. Our data parallel algorithms, like our parallel loops, these are composed automatically by the library for you into many, many tasks. So we create many tasks over decomposing our problem, which gives a lot of freedom to the TBB library to map these tasks to the available resources on the platform. So that's one thing that TBB uses to be composable. It uses tasks. The second, it has a pool of worker threads. So unlike some models like OpenMP where you encounter a parallel algorithm and it creates new threads, TBB uses a limited set of worker threads for all the parallelism you express in your application. So the many tasks that we create in our algorithms are all sent to workers in this pool. By default, the library creates one thread per logical core, and all of our parallelism uses these same worker threads. So if we're nesting parallelism, we're really just creating more tasks, and these tasks get mapped by the library to one of these worker threads when it's available to do work. So we're never oversubscribing our system by expressing more parallelism with TBB. And the last that is unique, well, for some libraries that are composable, is the way that we do scheduling in TBB is through work stealing. So we have our tasks, we have a pool of worker threads that can do work, and then we have each worker thread independently finds the work that it needs to do when it needs work. And it does this using a dispatcher, and inside of the dispatcher there's a data structure. And I'll go into a little bit of detail about how this data structure works, how each individual thread is matched up with one of these dispatchers and how it finds work through work stealing. But the benefit is that one of these worker threads, if it's executing on one of your cores, if the core is highly loaded, this thread is just scheduled less frequently by the operating system. So it's going to steal less often. So you're naturally going to have an overloaded resource just taking less work to do. Secondly, if a workload is imbalanced, so you have expressed a loop and the iterations in the loop have different amounts of work in them, this is fine. So as a worker thread becomes idle, so if you can think of this as one of your cores, doesn't have any more work to do, it's going to actively look for more work to do and steal away work from other threads that may have excess work to do when they're falling behind. So all these properties lead to good execution behavior for TBB, and it means that you can create lots of tasks, you can mix different components together that are using TBB, and TBB, the library, will just sort this all out and give you an efficient execution. So let's look at a loop. So we already saw in our Mandelbrot example a parallel loop. So here's another one. This one's even simpler. So using TBB, we're saying here that we want to execute a for loop in parallel. It has a range from 0 to n and a step of 1. So it's going to just increment from 0 to n by 1. And at each value in this range, it's going to apply this lambda expression where it's going to call a function f on each element of an array or vector A. Okay, so at the bottom we have this diagram. And what this represents is are the different tasks that the threads may execute. Each task is labeled T0 through Tn. So initially, when this loop is encountered, there is task 0. Task 0 represents the entire iteration space, so 0 to n. And so the calling thread is going to go to execute this task, and it's going to decide, based on a policy, that this is too much work for it to do by itself. So it's going to split the work into two pieces, the left side of the range and the right side. And it's going to pick one of these to keep working on. It's going to pick task 1, so the left side of the range. And it's again going to execute a task. The task, in this case, is going to look at this range. It's going to decide, this is still a lot of work to do. I'm going to further recursively divide this into two pieces. And so it creates two more pieces, T3 and T4, and it's going to pick one of those to work on. It's going to pick T3. And again, ask the same question. Is this still too large? And it is. So it recursively subdivides it. So eventually it gets down to tasks that I think are of a good size. And it's going to start to apply the lambda expression to these subranges. So it's going to start executing the lambda expression that calls f on these subranges. Now, while thread 1 is doing this, there are other threads available potentially in the system. So let's say while this is happening, a thread that's available to help out. So in this case, we have this other thread, thread 2. So thread 2 will just look around for work that's available in the system. In this case, it just picks T2. And it sees that there's a part of the range that's available to execute, and it will steal this from thread 1. So it gets this, and it does a similar process like thread 1. It looks at the range, sees it's too big, recursively subdivides it until it gets down to pieces of work that are of a good size to execute based on some policy. The important thing to note here is thread 2 made a really good choice about what to steal. So if you think about what's happening in our loop, we are processing an array. And you would want to, because of the way memory and caches are organized, you would want each thread to operate on a contiguous set of values. And if a new thread comes along and wants to steal work, it probably wants to steal something that is far away, not contiguous with what the other thread is working on. And that's what thread 2 did here. It picked a large piece of work, and it was far away from what thread 1 was working on. And this is something that's going to naturally happen based on the way that the TBB task scheduler is architected. Now, if we had other threads, they could come in and they could iteration space as well, working on them. Now, I said that this naturally, with the way that the TBB scheduling occurs with its work stealing, and I'm going to walk through a simple example just to show how that might occur. So here we're walking through the same example, and we're just going to look at how thread 1 and thread 2 interacted. And each thread is operating independently. And what they have is they have a double-ended queue in their task dispatcher. And when a thread needs to get work, it first looks at its own local queue, and it pops from the head of that queue. So this is the most recently created piece of work it's going to grab. If, however, there's nothing in its local queue, it's going to look around randomly and steal from some other worker thread. And when it does this steal, it's going to take the oldest thing that was in that other thread's queue. So here now we can see how we get this really good distribution of work between these two threads. So thread 1 initially had task 0. It splits it into 2 pieces, and it puts it into its local queue. Thread 2 has nothing to do, so it decides it has to steal something. So in our second time step here, thread 1 has popped something off the head of its queue, and thread 2 steals something from thread 1 because it stole something really large, stole what is T2 here. And after this point, these threads never have to communicate with each other again. And if you're familiar with what you want to optimize in parallel programming, is often you don't want things to be communicating with each other. And so we have a good property here as well. So now in the future, thread 1, which is working on task 1, does its splitting. It puts its 2 subtasks, T3 and T4, into its local queue. And it just, from this point on, pops things off of its queue, spawns new things into its queue, and so on, working on things independent from thread 2. Thread 2 now has enough work as well. It pushes new things into its queue, pops them off its queue, and so on. And what's great about this kind of behavior, where each thread is operating independently, it means that threads, when they become idle, they can move on to new work by just stealing things. Threads can come in and out of the system dynamically. So if some core is oversubscribed and a thread doesn't participate much in the work, it's not going to be stealing. So you get a lot of good properties that lead to composable execution. TBB is a composable library because it uses these tasks, a pool of worker threads and work stealing. So nested parallelism just works. You can create a lot of small tasks, and they'll execute on the limited number of threads in the pool, and you're not going to oversubscribe the hardware. And you can nest libraries that use TBB for parallelism without worrying about it. Now, typically, we're not going to be, as end users, creating tasks explicitly. We're going to be using these parallel algorithms that are higher level to create tasks for us. But it's nice to understand what's going on underneath that makes TBB a good choice for expressing your parallelism. So TBB, because the worker threads find work for themselves when they're idle, The scheduling that TBB does is resilient to dynamic load on the platform. As some resources become more loaded, they steal less. If they're very busy, other threads will eventually steal all their work away from them. The scheduling is resilient to load imbalances in the algorithm. If you express an algorithm that is imbalanced, that's okay, because threads that run out of work really quickly, they're just going to steal away work from other threads. And the other good thing about using tasks is we're able to over-decompose our problem, create a lot of tasks, more than would be efficient if we had to create threads. So we can create a lot of these lightweight tasks, which allows our algorithms to scale as more cores become available. So as more worker threads and cores are available, the tasks just get more widely spread across these workers. So TBB's generic, they all are implemented on top of tasks. So we're not expressing things directly with tasks. We're using these higher level algorithms, but we get all these good properties because they're implemented on top of tasks. And this is also true of the high-level execution interfaces within TBB. So the next one I'm going to talk about is the Flow Graph API. But it's important to keep in mind that all of the parallelism that we express using a flow graph also executes as TBB tasks. So if you're using a flow graph and you're also using parallel loops from the generic parallel patterns, they're all going to execute within the same thread pool. They're all going to compose if they're nested within each other, and you're going to get good, efficient performance that takes advantage of the available resources in your platform. This is about expressing graph-based parallelism. Graph-based parallelism is really useful. So this lets us express parallelism that might exist at a higher level of our application, or it may just be parallelism that is less structured than a loop. So for example, we have here on the left, we have a while loop. And so this while loop is reading images, either from a file or a camera, and then it's applying a series of filters to these images. So it reads in an image, it applies F1 to the image, gets a result X, then it applies F2 to X to get Y, and F3 to X to get Z, and then there's a fourth filter, F4, that is applied to the results Y and Z. So in our serial application, that's what the loop would look like. If we take the effort to express explicitly the dependencies between these filters and the reading of the image as a graph, we expose a lot of opportunities to a runtime library like TBB. So if we think about this loop, we can express it as a graph, as is shown on the right side of this slide. So graphs, in the graph, we're expressing the computations like the functions as nodes, and then the values that are passed between them as edges. So here, if we're looking at the while loop and the graph, we see that we're reading in an image, we're passing it into F1. F1 generates a result that is forwarded on to both F2 and F3. And F2 and F3 each generate results, Y and Z, and these are passed on to F4. So we're just expressing in a different way what we see in the serial loop on the left. But once we've done this, and I'll go into the details of the syntax on the next slides. So this is just looking at a high-level picture of what we will do with the TBB Flow Graph API. But we have equivalent things here, this left serial implementation and then this description as a graph. So once we describe the dependencies as a graph, we have given the operators and their input-output dependencies a runtime scheduler like TBB can exploit many different kinds of parallelism. So a runtime library could detect that the functions F2 and F3 can be executed independently on X because they don't depend on the output of each other. So F2 and F3 are not dependent on each other. They're only dependent on the output of F1. So a library could schedule these two functions in parallel on the same piece of data on X. Similarly, it could infer that if you could read images fast enough, you could actually stream images through this graph. So we could have first read an image 0 and sent it through this graph like a pipeline. And as we read image 1, we could also start it now in the graph overlapping the execution on image 1 with image 0. And we can continue to do this with subsequent images. So it At some point we could have image 2 being in some stage in this graph, image 1 and image 0. And that's called pipeline parallelism. And we could also exploit data parallelism. So we have this function f2, for example. We could, because we know its inputs and its outputs, we could execute it in parallel with itself. Or we could, as we've mentioned before, we can nest other kinds of parallelism within this node. So if, for example, f2, the implementation of f2, included a TBB parallel 4, that would be fine. That will nest efficiently and effectively within the outer graph. So what is the syntax? So the threading building blocks flow graph API is an efficient implementation of dependency graphs and data flow graphs. It lets us express this higher level parallelism in our applications. And the nodes, as I said, execute as TBB tasks, and so the execution is going to be composable. So on the right, we see a real simple example. It's a hello world kind of example. There's actually no parallelism in this particular example as expressed, but it shows you what the syntax looks like. So we have a few basic concepts in the flow graph API. We have the graph object, which is a handle on which we can wait for activity in the graph to complete. We can catch exceptions there. We can cancel a graph through the graph object. And then we have nodes, which represent the computations. These are the user computations, and we as well have some predefined nodes that do particular kinds of work. And then the edges. The edges represent either dependencies, like before-after relationships, or communication channels over which data flows. So coming back to our hello world example on the right, we create a graph object. This is our handle to the activity in the graph. Then we're going to create two nodes. And these are particular flow graph API node types that are useful for representing dependency graphs. So we're going to create a continue node named H, and we're going to pass to it a reference to the graph it belongs to and a C++ lambda expression that represents the work it does. And in this case, it just prints hello. Likewise, we're going to create a second node, W, that also receives a reference to the graph it belongs to and a C++ lambda expression for its work, which is to print world. After we create these two nodes, we make an edge between them. And we're expressing here a before-after relationship. So we're saying after H executes, W should execute. So H is the predecessor, W is the successor. Thereafter, whenever H receives a message, and it's of a special message type because this is a dependence graph, and all of this is more clearly and in more detail defined in the TBB documentation. But H receives a message, it executes, it spawns a TBB task to execute its body. This task is spawned, and one of the TBB worker threads in the thread pool will pick it up and execute it. When that work is done, so when the body of H is complete, a message will be sent from H to W, triggering W to execute its body. And it does this again by spawning a TBB task that gets scheduled onto one of the TBB worker threads. And lastly, in the example we call wait for all on G to wait for all of the activity in the graph to complete. The TBB flow graph can be used to create data flow and dependency graphs, as I said, and even heterogeneous graphs that execute on the CPU and offload work to accelerators. And to support these different kinds of graphs and different kind of use cases, there are a number of node types defined in the API. There are some for functional, there's some that are functional nodes. These encapsulate user code. There are some that do splitting and joining of messages into tuples and from tuples. There are some that, if you need to do special buffering in your graph, which is useful in some specific scenarios, you can add explicit buffers in your graph. And then there's some other utility kinds of nodes. So I'm not going to go into a lot of detail in implementations of TBB flow graphs. There are examples available in the TBB distribution, and there are other examples available online, And there's also videos that you can watch that go into more detail about the implementation of TBB flow graphs. But what I'm going to show here are just some high-level use cases of where it's applicable and where we've seen useful performance from using TBB flow graphs. So here's an example use case of a streaming graph that was used in an advanced driver assistance system, an ADAS application. So this looks like your classic image processing pipeline. Inputs are read from a sensor, in this case a camera, and these are frames. And then there's different algorithms that are applied to the frame. So in this case, there's lane departure warning, object recognition, front collision warning. And each of these algorithms are looking for specific things within the frame and will create the region, will compute the region in the image that demonstrates this. So for example, it will detect where the lanes are, or will detect objects in the frame. And then lastly, these results are merged together and overlaid on top of the original image to provide output to the user. And so the result is displayed. With a TBB flow graph, this can be expressed as you would expect. You have some node that is reading image data from a camera. You have other nodes that encapsulate the particular algorithms for lane departure, object recognition, front collision warning, and then you have a node that does the display. And these are all interconnected through edges, and in fact, nested TBB parallelism can be included in the workloads. So you can directly express this parallelism that exists in your application, and then leave it up to TBB to decide how to exploit this parallelism in conjunction with the nested parallelism. And there is an article that is referenced at the bottom of the slide that you can look at to get more information about this particular use case and its performance. Another example use case for a flow graph is linear algebra or matrix computations. So here we have a very simple forward substitution that's going on. So we're solving AX equals B. We're in a lower triangular matrix. And so we have this doubly nested loop, an I loop and a J loop. And in each loop, we are using previously computed values for X to compute the next value of X. So we're substituting, forward substituting back into the equations. If you were to look at the dependencies between all of the computations here, they would look like what's shown on the right. So we execute I, j equals 0, and the output of that is needed by 1, 0, 1, 0, so I equals 1, j equals 0, generates results that are then needed by 1, 1, 2, 0, etc. So if we plot out all of the dependencies for this particular loop nest, it looks like what's on the right. And you can see there's a lot of dependencies here. It doesn't look like there's much parallelism available. But if you carefully look, there is a wavefront that can be executed through this algorithm, and this green line shows an example of several nodes here that could be executed in parallel because they do not depend upon each other. So this is an example where using a TBB flow graph, you could express all of the dependencies between these computations and just let the TBB library sort out when it is safe to execute each part of the computation. Now, an astute reader, you may notice here that the inner loop could be expressed using a parallel reduce. So we could do a reduction. What's happening inside this loop, this inner J loop, is a reduction. We're computing the sum of values and storing them into B. So you could use a loop level algorithm to express this. And this is what happens in many matrix computations, but the result is that we're going to have that is parallelized. And between each execution of this inner loop, we're going to have synchronization points. So this leads to a suboptimal execution. We're going to have a lot of synchronization points, not a lot of parallelism between each synchronization point. By expressing all of the dependencies using a flow graph, we actually, the library can run ahead and execute tasks whenever they're ready to execute. Over the last couple of years, we've been extending the TBB Flow Graph API to support offload to heterogeneous devices like accelerators. I'm not going to go into much detail in this presentation, so I would refer you to additional videos that we're going to post and TBB documentation. But the basic idea is that the flow graph can also be used not only to express parallelism that should be executed on your host CPUs, but you could also use it to encapsulate computations that should be offloaded to devices like GPUs or FPGAs. And there have been features added to the flow graph API that allow you to express that these should be offloaded asynchronously to these accelerators. And it simplifies the process of doing that for you. High-level execution interface that I'm going to discuss in this presentation is Parallel STL. Now, Parallel STL refers to extensions that are in the recent C++ standards. So C++ 17 has added execution policies to the standard C++ template library. Now, the C++ standard template library, which is just part of the C++ standard, provides algorithms that operate on containers and iterators. So these are very useful for operating on sequences that iterate through containers. So an example on this slide, we're implementing an increment using the STL function transform. So we call transform and we pass into it a beginning iterator in, an ending iterator for the input in plus n, and then a beginning iterator for where to put the output, and then we provide a C++ lambda expression. So the STL transform function is going to iterate from in to in plus 0 and invoke this lambda expression on each value that it receives when dereferencing the input iterators and write that result into the corresponding position pointed to by the output iterator. It's just basic serial C++ STL algorithms. What is new is Parallel STL. So in the most recent standard, C++ 17, STL, the C++ standard library, has been extended with execution policy arguments. These arguments allow us to express how we want the algorithm to be executed, whether we want a sequential execution, a parallel threaded execution, a parallel and vectorized execution. There are different execution policies. And there are also parallelism technical specifications that describe other policies, such as just execute vectorized. So on the right side of this slide, we see different policies that are in the C++ 17 standard as well as in parallelism technical specifications. And these are ordered from the least constrained to the most constrained. So at the bottom we have a sequential policy that says execute this sequentially or in sequence order. And then we also have policies that are for threading, parallel, and policies that are for SIMD or vectorization. What do these all mean? So the default or sequential execution means that the operations for your algorithm have to execute in some sequence order. Many algorithms define the sequence order as an indeterminate sequence, but it means that each operation is executing on a single thread, and one operation executes to completion before the next operation starts. That's the default sequential policy. There's also a par policy, which means that you can execute the operations in parallel on different threads of execution. There's the unseek policy, and this means that you can only use a single thread of execution, the calling thread, but you're allowed to vectorize. So you can overlap the execution of different operations, of your operations, within that single calling thread by using the vector registers in your cores. And then lastly, the most unconstrained policy is that you can do all of those. You can execute using multiple threads of execution, so you can use multiple cores, and then within each core you can also overlap your operations using vector parallelism. The syntax for this is pretty simple. You have your original kind of STL algorithm like sort. So in this case, sort is being passed the beginning of a vector and the end of a vector. With Parallel STL, you just add an additional argument, the policy. So you can explicitly say, I want this executed sequentially by passing in seek. You can say you permit parallel execution with par. You can permit vectorization and parallelization, par and seek, or in the technical specification, you could say, I only want this executed vectorized. With TBB, or Parallel Studio XE, you get an implementation of Intel's Parallel STL, and it executes its parallelism using TBB tasks. So when you ask for a par or par unseek policy, then you get an implementation that is going to use TBB tasks to implement the parallelism. And this is good because it becomes composable with all of the other algorithms you've implemented using TBB. If you use a policy that requires vectorization, it's going to be implemented using OpenMP SIMD pragmas to allow execution on the vector units within your core. Now, Parallel STL includes many algorithms, but these are more specialized than the TBB generic algorithms. So often they're doing a particular kind of thing, like the algorithm could be a fill, a find if, a copy, something that's doing some very specific kind of work. Now there are some more powerful functions like for each, transform, reduce transform, but even these are less expressive than the generic TBB parallel algorithms because they work on sequences or containers, and often there's a limited number of sequences or containers, like for example, transform a single output sequence. So if you are wanting to write a general loop where you are iterating for some range and you're writing to multiple arrays or containers, it's just awkward to express that with Parallel STL. So this is one reason why when you're doing general parallelism, it's still very likely easier and more effective to use TBB. But for particular algorithms, Parallel STL can be very effective. The second reason, an additional drawback for Parallel STL is that many of the optimization hooks that we didn't cover in this presentation, but you can see in TBB documentation, there are optimization hooks within TBB that just do not have analogs in Parallel STL. So TBB gives you easy ways to create ranges that are tiled. It provides options for how your loops are partitioned, and other advanced features that there just isn't an interface for in Parallel STL. So when you have a part of your application that could be expressed both with TBB or with Parallel STL, you really have to think carefully about which you want to use. A Parallel STL is part of the C++ standard, so it's arguably more portable. However, it does have limitations. It's less expressive, and also there's less hooks for tuning your performance if needed. I'm just going to cover a few other features of TBB that are not part of the parallel execution interfaces. One is the concurrent containers. So TBB provides high-level thread-friendly data structures. So here's an example of a sequential application that is using a standard queue. And if you see here, the operation that's happening is the queue is checked to see if it's empty. If it's not empty, an item is taken from the front of the queue, and then it's popped. So this is a series of 3 operations that are performed on this queue, and it doesn't happen atomically. So if any other thread was involved in looking at this same queue, it could come in the middle, for example, after the first thread is checked to see if the queue is empty. Another thread could come in and empty out the queue before the thread goes on to grab what it thinks is the front of a non-empty queue. So these lead to situations where you have to do locking and awkward things. The parallel data structures, the concurrent data structures in TBB just provide high-level thread-friendly interfaces that are well-tuned. So for example here, a TBB concurrent queue in contrast has a try-pop function. So it does all of those necessary operations in a single atomic function. Interesting feature of TBB is its scalable memory allocator. TBB provides useful memory allocators that are often useful in parallel applications. For example, one thing you may want to do in your parallel application is to make sure that your data is correctly padded so that it's aligned on cache line boundaries. And TBB provides an allocator that does that for you. On some OSs, when you allocate memory, it's all happening from a single global heap. And so if you have many threads that are allocating in parallel, you can have overhead because you have contention on this single global heap. So TBB provides also a scalable memory allocator that uses per-thread heaps to avoid this locking overhead for you. And if you want to use and try out the TBB scalable memory allocator, there's also support in the library to do automatic replacement of new and delete and malloc and free. So it's a very easy thing to try out. And I would ask you to look at the TBB documentation or the threadingbuildingblocks.org or videos found there to see how you can do that. It's fairly straightforward. In conclusion, TBB is a set of building blocks that can be used to simplify the expression of parallelism in your application, to take advantage of the available resources, the multiple cores you have in your platforms, and it provides this through a set of high-level parallel execution interfaces that are built on a shared set of low-level interfaces that allow them to be composable with each other and to get high performance, and then also a set of interfaces that are independent of the execution model, like our containers and scalable memory allocator that I discussed here. About TBB, at the websites, threadingbuildingblocks.org or software.intel.com/IntelTBB. There's also some good articles available in Intel Parallel Universe magazine. There's a issue shown on the left that came out a little while ago to celebrate TBB's 10th anniversary. And this particular issue talks about the history of TBB, the important parts of TBB, how it's evolving, and the whole issue is dedicated to TBB. It's a really good place to start if you're interested in learning about where it came from, what its philosophy is, and so on. And then there's also the issue shown on the right that talks about that example that I showed of the ADAS workload and how that was expressed using a TBB flow graph. I think at this point, I think we'll open it up for questions.
Great. Thank you, Mike. We do have a few questions that we'll be able to get to. The first question is, you've said that OpenMP is not composable. Does this mean that OpenMP should not be used? Or are there cases where OpenMP is better than TBB and vice versa?
Yeah, so that's actually a very good point. So OpenMP was first introduced back in 1997, and at the time that OpenMP was introduced, the world was different. So there was parallelism was exploited against supercomputers and servers that were dedicated for solving problems. In contrast, TBB was introduced around 2006, and at that time, Intel had already introduced the first multi-core laptops and desktops. So the environment was different. OpenMP was really about high-performance computing and assumed monolithic programs. TBB was now in an environment where you were running on desktops and laptops, where you might have your virus checker running in the background, your web browser. You might have a more dynamic environment that was shared. And so OpenMP still is often used in HPC applications because it has a simpler model that is based on threads, and it relies on, in many cases, static scheduling across the threads. So in the case where you have the whole system is dedicated to your workload, you have sort of a flat parallelism, not nested parallelism. OpenMP can, with very simple pragmas, can get you highly efficient, effective code. If, however, you're in a more dynamic environment where you're executing, there are other workloads executing with it, you're building composable software where you're combining a bunch of components, then TBB is able to deal with that dynamic nature more. Also, OpenMP, although it has bindings for C and C++, it's pragmas, and some C++ developers just don't like using pragmas. They would prefer to use a C++, a pure C++ library like TBB. So they do each have their niche where they perform really well, and there may be just preferences based on whether you like pragmas or a library as well.
All right, thanks. The next question is, does TBB optimize for NUMA architectures?
So TBB has many default behaviors that are optimized for locality. So I hinted at some of these earlier when I talked about how a loop was broken down into tasks and how threads would steal tasks. So there are some behaviors in TBB that are tuned so that you get good behavior where threads steal things that are not close to other threads, and then they work on work that they've generated until they run out of things. So a lot of times this gives you good locality behaviors. For NUMA, sometimes you need to do some extra work to make sure that things are placed in the right places on your system. And TBB provides hooks for controlling that as well. So, for example, there are hooks that allow you to intercept when a new worker thread is created, so you could pin things explicit if you wanted to. There are explicit task arenas within TBB that you can use for creating different, for dividing up your threads into different isolated groups, so that you could issue some work into one task arena, different kinds of work into a different kind of different task arena, and you could pin the threads in those arenas to different parts of your platform. So you have a lot of control. You can have a lot of control with TBB if you start to use those hooks to express the way you want your threads mapped to the hardware. So it's possible with TBB to do NUMA, and as I mentioned earlier, however, many of the default behaviors of TBB lead to a pretty efficient execution without even using hooks.
All right, thanks. We have time for a couple more questions. First, can I assign priorities and affinity to nodes in a TBB flow graph? So my answer for this is similar to the previous answer. There's a lot of default behaviors within TBB that in many cases get you the performance that you need. So for example, in a flow graph, nodes will follow, threads will follow data through the graph. So there's oftentimes you'll get the behavior and performance that you want without having to use any kind of special hooks.
We currently do not have support for affinitizing a particular node to a particular thread, but there are ways with some of our asynchronous offload features to create this kind of behavior manually. We are also looking at extensions for affinity and priority in the TBB flow graph. So if there are customers out there who are interested in those features, we would be really interested in hearing about your use cases. So please reach out to me because we're in the process of designing support for adding priorities and affinity to nodes in the graph. You can currently express priorities for a particular graph, but not for individual nodes in the graph.
Okay. And we have time for one last one. What about features in the C++ standard like standard thread, standard async, standard feature, etc.? What does TBB provide that C++ itself does not?
Yeah, so this is a good question as well. So so the C++ standard evolves over time. There are different versions of the standard. So C++ 11, which is widely available in compilers now, introduced some basic building blocks for threading. So you have async and future, you have standard thread, but these are really low-level building blocks. So I would say they are similar to that low-level interface that I showed in the block diagram for TBB. It's not something that most developers want to be using directly. These would be things that if you were going to use them, you'd wrap them in something anyway. So C++ 11 was good because it started to address threading. Previously, the standard was just silent on threading. So it was a big improvement, C++ 11. But still, it didn't give the high-level interfaces that you'd want to use. C++ 17 has started to raise the level of abstraction for programmers through those execution policies that I mentioned. But as I also mentioned when I was talking about Parallel STL earlier, these are still awkward in some use cases. And if you're not operating on a small set of sequences or containers, it can be difficult to express what you need with Parallel STL. And also, TBB has recognized over the years, TBB is over a decade old, has recognized that there are important hooks that are needed for tuning performance when you're really interested in getting the highest performance. And those hooks just don't exist in Parallel STL currently. So you can say, I want a parallel execution, but that's about it. There are ways to provide custom execution policies, but if you're keeping just with the execution policies in the standard, there's not a lot of performance tuning you can do with those. Now, upcoming in future standards for C++, there are other features that are proposed for inclusion, like parallel loops, task blocks, executors, resumable functions. There's a lot of new features that are coming to C++ in the future. Many of these actually depend upon some underlying implementation to implement the parallelism. Just like with Parallel STL, you express, I want parallelism, but the standard doesn't say how it's implemented. There has to be something underneath that is the execution engine. So I think looking forward, how TBB will likely evolve is TBB, as those things become available, TBB will provide an execution layer for those features. That hasn't happened yet, and the standard's not standardized. So that's what I'm just thinking is how things will evolve in the future. TBB has always been, the team that develops TBB has always been interested in getting parallelism features into the C++ standard. I mean, that's our end goal is just to make it easier for C++ developers to thread their applications. So we closely track the standard, and we try to provide either early implementations of features that are going into the standard, or in the case of these future features, we're looking forward to providing support to make those features execute really well on Intel hardware.
All right, great, thanks. So thank you everyone for sending in your questions, and thank you for joining us today for this webinar on TBB. And again, you'll be able to find a lot more information on TBB and other Intel software tools on the Tech-Decoded website. The link is right here. You'll be able to see other webinars such as this one, and also some quick hit short videos and articles that will give you more of the how-to specific information. So again, please join us there on the Tech-Decoded site and look at all the great resources that are available there. So again, thank you everyone for joining us, and we appreciate your time and hope that we'll be able to see you at another webinar very soon. Thank you, everyone.